Hi all, let's start with today's problem solving session. I'm Clarice. I will be here today here for the problem solving session 5 for the course Spectroscopic Techniques for Pharmaceutical and Biopharmaceutical Industries. I hope all of you can hear me. Let me know if you are not able to hear me. Um, I hope the slides are also visible for you all. Can someone text in the chat box? That would be great. Yes, thanks. So this week, the course was dealing about atomic spectroscopy, and it deals with the transition between electronic states of atoms. And the fine in the lecture, we have found the energy of atomic levels by solving Schrodinger equation, and yeah, so this is the Schrodinger equation which we have started on during the at the beginning of the lecture, uh, where um, where we have considered the kinetic energy of electron and kinetic energy of the nucleus, and the potential energy of the system to calculate the energy of the system. If we know the wave function associated with the system. So solving this Schrodinger equation is not very straightforward. Hence, we went ahead with separation of motion into two parts. So we considered two different. Okay. So we considered two motions where yeah. So we considered two motions where one is the relative motion of the electron, and the other one is the uh, translational motion of the center of mass itself. And we came to this then we came to this particular um, then we came to this particular Schrodinger equation where we have considered the kinetic energy with respect to the center of mass, and the kinetic energy associated with the relative motion of the electron, and also the potential energy associated with the relative motion. Um, then then they have calculated the we further progressed in this direction to find the in this direction to find the um, find the energy of atomic levels. And yeah, so uh, after after we have simplified this Schrodinger equation, we came to this particular expression of Schrodinger equation. So where U of R is the radial part of the wave function, and yeah. So upon solving this Schrodinger equation, we will be able to get what is the value associated with the E, which corresponds to the energy of the atomic levels. So the I'm not deriving it anything particularly. I'm just giving the equations that we have covered in the lectures. So for hydrogen atom, uh, L is going to be equal to 0, which is the and N is going to be 1, because we are dealing with the 1s1 electronic configuration. And yeah, so for a 1s1 electronic configuration, we'll have N is equal to 1 and L is equal to 0. And the Hamiltonian operator, when we substitute L is equal to um, when we substitute L is equal to 0 in this particular Schrodinger equation, we'll get the Hamiltonian operator like this. And from this equation can have one of the solution like this, where U of R is defined as R e raised to minus sorry R is e raised to U of R is equal to R e raised to minus gamma R. So upon solving the Schrodinger equation by putting in the U of R, by putting in U of R in this Schrodinger equation, we will be able to obtain what is the value for um, energy. So that sorry, yeah. So that is coming to okay. So that is coming to energy is coming to us minus mu 2 by h cut square z square e raised to 4 by 4 pi epsilon 0 square. And for hydrogen like atoms where sort of n is not equal to 1 but n is equal to 0, the Hamiltonian operator will be the Hamiltonian operator is same as hydrogen atom, but when we can have another solution for this uh, for this particular Schrodinger equation, which is given by U of r is equal to r minus r square gamma e raised to minus gamma r, and the energy of the system is going to be represented upon substitution of this wave function in the Schrodinger equation. We can find what is the value of E, and the E has come out to be minus mu 2 pi 2 h cut square n square z square e raised to 4 pi 4 pi epsilon 0 square. So with this sort of says that E is inversely proportional to 1 by n square, right? Mm. So this is the Hamiltonian operator for any particular atom which has some L not equal to 0. So this is the Hamiltonian operator for any atom which has any value of L and N. And upon we just have taken a particular example where L is equal to 1 and N is equal to 2, how our energy value is going to be. So for the particular Hamiltonian operator, the wave function, the potential solution can be U of r is equal to r square gamma e raised to minus gamma r. Upon substituting this u into this into the Schrodinger equation, we will be able to obtain what is the E value. And the E value is coming out to be same as when even when how the how we solve the energy value when the L is equal to 0. So this says that L is independent of E is independent of L, right? So So for any system, for any atom, we have found what is the radial part of the wave function going to be. This is directly from the lecture, and we have a initial part which is determined, which is sort of a constant for any system, any particular NL value that you're defining, and the energy is independent. As the energy is independent of L value, it is just dependent on the N value. So the energy can be even when you calculate, even when you give any particular L value, L can be like ranging from 0 1 to any particular L value, we still end up with the um, energy value to be minus mu 2 h cut square n square z square e raised to minus 4, e raised to 4 by 4 pi epsilon 0 the whole square. So here you can see that in the wave function that we have defined, there is a um, one second. Yeah. So there is a polynomial associated with it, which is called as Legoric polynomials. So this can be defined for any particular atom. So if we know what is its L or N value, so so this is the one which is corresponding to Lagrange polynomials. And yeah, this is the one which is corresponding to Lagrange polynomials, and you can see that LPQ of x is equal to d raised to p by dx raised to p LQ of x, and LQ of x is another polynomial which is again defined by a couple of other variables like e raised to minus x uh, is defined by the variable x, but it has the form of e raised to minus x d raised to q divided by dx raised to q, acting upon e raised to minus x raised to q, and the p and q are defined by L and N respectively. So, sorry, P is defined as 2L plus 1, whereas Q is defined as N plus L. Let's define the Lagrange polynomial for 1s1 orbital of hydrogen atom. So, if we have 1s1, which means N is equal to 1, L is equal to 0, right? And yeah, so P is going to be 2n, P is equal to 2L plus 1, so that is going to be 1 because L is equal to 0. Q is equal to N plus L, so that is going to be 1. So LQ of x is equal to, so this a couple of them has been solved by professor in the class. I think 1s1 itself has been solved in the class. I'm just solving so that you get familiarized with it. So LQ of x is equal to e raised to minus x d raised to 1, since q is equal to 1, dq raised to 1, e raised to minus x into x. So this is going to be e raised to minus x. So we have to differentiate it by parts. So here, so this is going to be d by d. So yeah, d by dx of e raised to minus x multiplied by x plus e raised to minus x d by dx of x. So first function in derivative of first function into second function plus second function in first function into derivative of first. So this is going to be e raised to minus x. E raised to minus x is going differential of e raised to minus x is going to be minus e raised to minus x into x plus e raised to minus x. D by dx, dx by dx is equal to 1. So this is going to be e raised to, okay, minus e raised. So it's going to be e raised to minus x, e raised to minus x plus e raised to minus x, e raised to minus x. This is going to be minus e raised to minus 2x. So e raised to minus x into e raised to minus x is going to be e raised to minus x minus x. This is going to be e raised to minus 2x. So e raised to minus 2x into x plus e raised to minus 2x. So this can be written as e raised to minus 2x 1 minus x. And now we have to find what is LQP of x. Here it is going to be L11 of x. So this is d by dx d raised to 1 as p is equal to 1. Then as p is equal to 1. So LQ here is 1, L1 of x. So that is, we already know what is L1 of x. It is going to be d by dx of e raised to minus 2x 1 minus x. So we can do differential by parts where derivative of first function into 1 minus x plus e raised to minus 2x d by dx of 1 minus x. I think I may need one more slide to solve this. Okay. So L11 of x is equal to d by dx of e raised to minus 2x into 1 minus x plus d by sorry e raised to minus 2x d by dx of 1 minus x, and this will be d by dx of e raised to minus 2x is going to be e raised to minus 2x into minus 2 because it has e raised to uh, so d by dx of e raised to minus e raised to x is e raised to x. Since it has x is another polynomial, we have to differentiate that and multiply it with uh, multiply it with the differential of exponential function. So here, so so that's going to be e raised to minus 2x d by dx of minus 2x into 1 minus x plus e raised to minus 2x. D by dx of 1 minus x is going to be, so this is d by dx of 1 minus dx minus dx. So this is going to be e raised to minus 2x. This is d by dx of minus 2x is going to be minus 2 into 1 minus x plus e raised to minus 2x. This is going to be 0. Any differential of any constant value is going to be 0. So 0 minus 1. So this will become e raised to minus 2x minus 2 e raised to minus 2x, and when it is multiplied to 1 it will be stay same. When it is multiplied with minus 2x it will be like plus 2 e raised to minus 2x into x, and you will have a minus e raised to minus 2 when this is multiplied with minus 1. So yeah, so this will become uh, 2 e raised to minus 2x into x minus um, 3 e raised to minus 2x. So this can be written as 2 2x minus 3 into e raised to minus 2x. So L11 of x is going to be this. Uh, so this is going to be the logarithm polynomial associated with 1 is 1 of hydrogen atom. We can find it for any other electronic configuration. If you have something like 2s2 or 2p1, we can calculate by substituting into the equation that is being given here. don't know why my internet is pretty slow. Whatever I'm changing is not. The the internet connection in my one of my devices is slow, so slow. So I'm not able to. Let's wait for like 2 minutes so that it come back to the slide where I'm currently in my device. So I'm at slide which where I have the equations for Liguori polynomials. Okay. Yeah. So here, if we have for any particular electron configuration, if you have n and l value, you will be able to calculate what is the Liguori polynomial associated with it. Uh, let's move on to the atomic spectrum of hydrogen atom. So we finally came to know what is the energy of atomic energy levels. So we know that E is going to be E is equal to minus mu. So E is minus mu H. So this is how the energy that we have found uh, from the uh, that we have arrived at by solving the Schrodinger equation. So we also realize that E is inversely proportional to n square for any particular system. It only depends on for a hydrogen-like system. It only depends upon the n square value. Hydrogen for hydrogen atom or hydrogen-like systems, E is directly proportional to n square. Otherwise, it will also depend upon z square. So for for any system, E is directly proportional to z square by n square, right? Where Z is the atomic, is the number of electrons present in the system. Okay. So now if we have to find the energy gap between these levels, uh, if we have to find the energy gap between these energy levels, we can also write this E in terms of minus mu e raised to 4 divided by 8h square instead of h cut square, where h cut is h by 2 pi. H denotes Planck's constant. So we have changed it to h square. That's why the expression is slightly different. It's going to be z square divided by epsilon 0 square, epsilon 0 square. Okay. Now, yeah. Now, when you're going to find the energy gap, in the lecture itself we have been given delta E is going to be minus 13.6, 1 by n2 square minus 1 by n1 square electron volt. And we can also find the wave number as minus RH 1 by n2 square minus 1 by n1 square. So this is in meter inverse. Um, yeah, so we can use either of these formulas to find the energy gap. So now I'm going to use this particular formula to find the to determine the shortest and the longest lines in the Lyman series. So shortest okay, shortest in wavelength says that it should be okay. So delta E is directly proportional to 1 by lambda, right? So when you have a higher energy gap between your N2 and N1, then you have when it is higher, then you have a lower lambda. When the delta E between N2 and N1 is lower, then you will have the higher lambda. So, so for Lyman series, the N1 is always equal to 1. So for the lower lambda, N2 can be anything, right? Delta, according to the selection rule, delta N is unrestricted. So it can go between, so for Lyman series, it can go between n is equal to infinity to n is equal to 2. So delta n2 minus n1 is higher when n is equal to infinity, and n is equal to 2 is when the energy gap between n2 and n1 is the lower. So basically we have to find what is the energy gap between the sorry, between the lowest and the highest uh, so for finding the shortest wavelength in the Lyman series, so we have to find when the wavelength associated with the transition between n is equal to infinity to n is equal to 1, and the other case we have to find what is the when the low shortest wavelength is highest wavelength is observed when in the Lyman series when the transition is between n is equal to 2 to n1 is equal to 1. So let's start the calculation. So I'm going to do it in this particular way by finding the wave number. So let's find the wave number first. And we know that lambda is going to be 1 divided by wave. So if we find what is the wave number using minus RH 1 by n2 square minus 1 by n1 square, we can find lambda. Okay, so RH is going to be 1.096 into 10 to the power 7 meter inverse, and for shortest lambda, we have for shortest lambda n is equal to n2 is equal to infinity and n1 is equal to 1 for Lyman series. For Lyman series, n1 is always equal to 1. Okay, so RH is going to be 1.096 into 1 divided by infinity minus 1 divided by 1 square. 1 divided by infinity is equal to 0. So this is, sorry, I forgot to add the exponent. RH is 1.096 into 10 to the power 7, 1 divided by infinity minus 1 by 1 square. So this is going to be minus 1.096 into 10 to the power 7. 1 by infinity is equal to 0, so it is 1 minus 1 by 1 square, which is minus 1. So this is going to be 1.096 into 10 to the power 7 meter inverse. Yep. I may need one more slide up here. Yep. So your lambda is going to be 1 by mu bar. So 1 divided by 1.096 into 10 to the power 7 meter inverse. So this is going to be 1 divided by 1.096 is 0.912 into 10 to the power minus 7 meter. So we can transfer it to wavelength to 91.2. This will be 91.2 into 10 to the power minus 9 meter. This is equal to 91.2 nanometer. Okay. This is this is for the shortest lambda. So for longest lambda, the n1 is equal to always 1 because we are looking at Lyman series. N2 is supposed to be 2. So nu bar is going to be minus RH 1 by n2 square minus 1 by n1 square. So this is minus 1.096 into RHS 1.096 into 10 to the power 7 meter inverse. So this is 7 1 by 2 square minus 1 by 1 square. So this will be minus 1.096 into 10 to the power 7, 1 square minus 2 square divided by 2 square into 1 square. So this is going to be minus 1.096 into 10 to the power 7. 1 minus 4 divided by 4. 2 square is 4. So this is going to be, let's do the calculation. 1 minus 3 into 1.096 divided by 4. This is going to be 0.822 into 10 to the power 7 meter inverse. So lambda is going to be 1 by mu bar. So that's going to be 1 by 0.822 into 10 to the power 7 meter inverse. So this is 1 divided by 0.822 is going to be 1.2165 into 10 to the power minus 7 meters. So this is going to be 121.65 into 10 to the power minus 9 meter. So this is 121.65 65 nanometer. So this is the longest lambda that we can longest wavelength length that we can observe in the Lyman series. So in this particular question, we have been asked to determine the shortest and the longest wavelength lines in the Lyman series. So for the Lyman series is defined as we are coming from an N2 to N1 where the n1 is equal to 1, n2 can be some any value greater than 1. And we have to find what are the value, what is the longest and the shortest wavelength in this particular series. So it depends upon the energy gap between the energy gap um, between the between the levels, and the highest energy when you have the highest energy gap, that's when you see the lower lambda. So basically it can come from, since the delta n is unrestricted as per the selection rules, it can come from even at n is equal to infinity. So when n is equal to infinity is when you have the energy gap highest, which in turn have the lowest delta value, so lowest lambda value. So that's why we have started for the shortest lambda value, we consider the wavelength associated with the transition from n2 is equal to infinity to n1 is equal to 1. The shortest wave, the highest longest wavelength will be observed when the energy gap is the lowest. So energy gap is the lowest between n is equal to 2 and n is equal to 1. So that's so we have to find the wavelength associated with the transition from n is equal to 2 to n is equal to 1. So that's what we have found out at the end. RH is the constant, that's been called as Rydberg constant here. Okay. So towards the end of the second lecture for the last week, we've been introduced to the hyperfine structure of hydrogen atom. So the introduction of total angular momentum because of spin orbit interaction, um, uh, introduction of total angular momentum because of spin orbit interaction, and the total angular momentum quantum number is defined as it can have values between L plus S to L minus S. And for example, um, if you have a P3 or P2 orbital, your um, yeah, P2 orbital, it is going to have like a L value of 1 and S value of yeah, S value of 1. So we can have total different values for spin angular momentum from 2, 1, 0. So it can have values between 2, 1, 0. So so for a system in P2 electronic configuration, it can have different values of total angular momentum 1. So this gives rise to initially the p orbitals has a degenerate uh, P2 has a degenerate energy level. It has been split to 3 of them, uh, something like this. I'm just giving you a pictorial representation. So basically, the degenerate energy levels has been split to 3 because of the presence of uh, spin orbit interaction. So the energy, the effect on energy levels due to spin orbit coupling has been solved using introduction of the Hamiltonian associated with the generation of magnetic field when there is spin orbit coupling, and the delta is he has been solved. So we have derived what is the Hamiltonian associated with spin orbit coupling. By solving the Schrodinger equation, we have found out what is the energy of stabilization or destabilization that will be introduced due to spin orbit coupling, and we also have told how to define any of these energy levels. For example, what sort of a name you will be giving any of these energy levels towards the end of the lecture. So let's look at one of the problems. So the term symbol for a particular atomic state is called as 4T 5 by 2. We have been asked what are the values of L, S and J, where L is the orbital angular momentum, S is the spin angular momentum, J is the uh, total angular momentum. So okay, so the term symbol is being given 2s plus 1 Lj, and S is corresponding to this, and L will be corresponding to the orbital angular momentum, J is corresponding to the total angular momentum. So J associated with this is going to be 5 by 2, 2s plus 1. So we can directly say that the total angular momentum, which is a subscript of this term symbol, can be directly taken as the total angular momentum. 2s plus 1 is given as the superscript, which is 4. So from which we can calculate what is S. So 2s is going to be 4 minus 4, 4 minus 1. So this is equal to 3. S is equal to 3 by 2. Then we have to find what is L. So if L is equal to 0, then it is going to be S. When L is equal to 1, then the term value is going to be P. When L is equal to 2, term value is going to be D. L is equal to 3, it is going to be F. So here the term value is B, which corresponds to L is equal to 2. So this says that the total angular, the orbital angular momentum quantum number is going to be 2, spin angular momentum quantum number is 3 by 2, and the total angular momentum is going to be 5 by 2. So then we have been asked to find what is the minimum number of electrons which could give rise to this particular term symbol. So we know that we need at least some 3 of the electrons to show this sort of a electronic configuration. So you have some 3 unpaired electrons. So every unpaired electron will have a S value of 1 by 2, and when you have like 3 of them, you will you have to add them to get the final spin angular momentum. So since it has to fill L is equal to 0, which has a S, P, it has to go till 2. It has to be either, it should have at least D orbital. So if you look at the electrons in the, if you look at the electronic configuration, when you have at least, so when n is equal to 1, it can only have s orbital. When n is equal to 2, it can have s and p orbital. When n is equal to 3, is when you can have sp and d orbital. So the current configuration should at least have n is equal to 3. So which means, and it has some three unpaired electrons in its d orbital. So this is supposed to be 1 is 1, 1 is 2, 2 is 2, 2p6, 3 is 2, 3p6, and 3p3, something like this. So the electronic the filling of electrons happens first in first orbital, where it will fill all the 2 electrons in the s orbital. So 1 is 2, 2 is then it goes to the second orbital, where it will fill it in the s subatomic orbital first, and s subatomic orbital can only have a maximum of 2 electrons, and then it goes to the p subatomic orbital in the second orbital, and it can fill a maximum of 6 electrons. Then it goes to third orbital, which can have s, p, and d uh, orbitals, and suborbitals. And we know that there is 3 unpaired electrons in p3, so it can fill 3s2, 3p6, then 3p3. So this is the sort of possible electronic configuration um, that we expect for this particular that we expect for this particular um, terms that we expect for the atom which has a term symbol 4d 4d. Okay. Next one is just to find the term symbols for the following pairs of electrons. So this we have already discussed here, right? Oh, I don't think so. I discussed. Okay. So basically we have to find what is the term symbol associated with it. The generalized form of term symbol is 2s1 Lj, and for A it is S square. So it's S2. So it has 2 electrons. 2s is going to be 1. L is equal to 1 because it only fills up S orbital. Then J is going to be L plus S is 2 till L minus S is going to be 0, 2, 1, 0. So it can have, okay, 2s plus 1 is going to be 2 plus 1, 3. So L is equal to 1 denotes P. Sorry. L is equal to 0. Sorry. It can have, okay. So it can have any values of L, depends upon what is your N values. So you can have L is equal to 0, 1, 2. So L can have values till n minus 1, right? So in this particular case, you can have different values of L. I will be writing for 0, 1, 2. So if L is equal to 0, then it is going to be S. L is equal to 1, then it is going to be P. L is equal to 2, then it is going to be T. So it is going to be 2s plus 1 is 3. So 3, uh, 3 is 2, or it can have 3 is 1, 3 is 0, and if this is when n is equal to 1. If n is equal to 2, then it will be 3p2, 3p, 3p1, 3p0. If n is equal to 2, n is equal to 3, it will be 3p, 3d, sorry, 3d, um, yeah. So this is how it happens. And if it is p square, which is not p square, p2, it is going to be s is equal to 1. Then L is going to be, L can be um, sorry, Yeah, so uh, one second. Okay. Um, yeah, there is a mistake. You can't have yeah, irrespective of wherever it is going to be, it is supposed to have only, yeah, irrespective of whatever value is your n, you can only have yeah, you can only have these three states, because your L is, for s orbital, your L is always 0. Sorry, L is always 0. So you can only have these three values, where L is equal to L is equal to 0, and S, the corresponding symbol associated with this with it is S. And okay, yeah. So for P2, it is going to, S is equal to 1, L is going to be 1, and J can be 2, 1, 0. So it is going to be 3P. When L is equal to 1, it is going to be 2S plus 1 is going to be 3. So 3P2, 3P1, 3P0. When it is d square d2, S is equal to 1, which implies 2S plus 1 is going to be 3. L is equal to 2. J can have, okay, here in that particular case my J values are also wrong. Sorry. Yeah. Uh, yeah. So let's first look at the first case, where is where you're looking for the term symbols associated with S square, S2 configuration. So in that particular case, S is equal to 1, L is equal to 0, and your J is going to be L plus S, which is 1, and L minus S, that is 0. Then the other one is 1, right? So I think you can only have L minus S is going to be minus 1, and the magnitude of L minus S is going to be 1 itself. So you can only have a J value of 1. So the term symbol associated with this uh, is 2S plus 1 is 3. So 3 is, because L is equal to 0, then 3 is 1. And in case of P2, S is equal to 1. So 2S plus 1 is equal to 3. L is equal to 1. As L and S both are 1, you can have a J values of L plus S 2 to L minus S 0, which is 2, 1, 0. So you can have 3P2, 3P1, 3P0. When the electronic configuration is D2, the S value is equal to 1, so 2s plus 1 is going to be 3. D is equal to 2, L is equal to 2. So J value can be um, L plus S, which is 3. L minus S is going to be 2 minus 1 is 1, right? So 3, 2, 1. So 3D 3, as L is equal to 2 is why I have the symbol as D. 3D2, 3D1. So these are the three values which are possible for these are the three values which are possible for these are the three values possible for D2, and for P2 we have three values, 3P2, 3P1, 3P0. For S2 we have only one possible value, which is 3S1. Yeah, that's all I have to discuss with you for today. If you have any particular question with the questions that we have discussed today, so let me just summarize what we have done today. Today we have today we have first discussed about the Hamiltonians that we have dealt at the beginning of the class, and we came to know how we have separated it to into two parts based on the motions that is happening, and we came to the Hamiltonian which looked like this, and then we have seen uh, how the Hamiltonian operator looked like for a hydrogen atom where L is equal to 0 and N is equal to 1, and how the wave function associated with it look like, and for how it is look like for a hydrogen-like atom. And we found that energy is inversely proportional to n square, and it doesn't energy of atomic levels are not doesn't depends upon the L value, and this is what we have finalized by looking at by deriving the energy value for L is equal to 1 and N is equal to 2, and we also have a generalized wave function using which you can calculate for any particular L value and N value the energy associated with any L and L value, and we so in the wave function associated with the energy levels associated with the atomic levels, we have found that there is a dependence to Legare polynomials, and how to define Legare polynomial for any particular atom if we know what is the L and N value of the orbital that we are looking at, and we have calculated how much is the what is the Legare polynomial associated with 1s1 hydrogen atom, and then we came to the atomic spectrum of hydrogen atom, and we have calculated what are the shortest and the longest wavelength in the Leyland series, yeah, using the wave number associated with the transitions. For a longer wavelength, uh, we have found the wavelength that is associated with n2 is equal to 2 to n1 is equal to 1. For the lower shortest wavelength, we have found the wavelength associated with the transition of n is equal to infinity to 1. Then we have come to the hyperfine structure of hydrogen atom, and we have calculated what is the LSJ values for a 4d by d5 by 2 state, and we have found the term symbols associated with a couple of electronic configurations. That's what we have covered today's problem solving session. If you have any particular questions, please raise it up. If you don't have anything, shall we end the session for the today?